Hello everyone, this is Ayşe Tekeş from Kennesaw State University. In this video, I will briefly summarize the mode ratios of a freely vibrating 2-degree of freedom system. You have learned this topic probably in your mechanical vibrations class, and you might also be familiar with this educational setup from your vibrations and control laboratories. So what I did, I designed a 2-degree of freedom translational system in my lab, and the system will not be forced. Instead, I will displace the cards to a displacement, and then I will release the cards. And you will see from here that the sliders, the cards, will be oscillating at their own frequency as expected. For a 2-degree of freedom translational system, you will see two peaks in the power spectrum associated with each natural frequency. But today the question is there any way I can control the frequency of oscillations by adjusting the initial displacement? So what I mean is, instead of randomly displacing the cards to a value, can I adjust the initial displacement so that the cards, I can control the frequency of oscillations of the cards as in the second video. So this is like a trick or a magic. So I initially tuned the displacements of the cards so that when I displace them, the cards will be just oscillating at one of the natural frequencies. And from the power spectrum, you will just see one peak on the screen, as expected. You probably have downloaded our virtual lab developed in MATLAB Simscape, and from here I designed exactly the same system or a very similar system. And if you randomly displace the cards, you will see that the cards, each of these sliders, will be oscillating at their own frequency, and you can plot the power spectrum from here, and that will show you two peaks, again associated with each natural frequency. In this example, the natural frequencies will be at 2.3 Hz and 3.2 Hz. But once I set the initial displacement to the first mode ratio, in this case it will be -1, then the cards will start oscillating at only one frequency, one of these initial natural frequencies. So here it will be 3.2 Hz. And similarly, if I set it to the second mode ratio, which was 1, because I designed a symmetrical system, then from here you will only see one peak in the power spectrum, although the system is 2-degree of freedom and you expect two peaks. So what is the theory behind this? Let's look at it all together. I will continue with my notes. I designed the same system in my notes so that you can consider this as a sketch of your system. And let's call the first mass as M1, the second mass as M2, the first spring K1, in between K2, and then the last spring as K3. And assuming also the second card displacement is measured by x2 and the first card displacement is measured by x1. So this is a multi-degree of freedom system. For 2-degree of freedom system, you need two equations representing the motion of the system. This card is only moving back and forth, only allowed to moving back and forth because of the mechanical limitations, and the second card is only also allowed to move in one-dimensional motion, back and forth. That means I can apply mass matrix method. Here, the inertia forces plus the damping forces plus the spring forces should be equal to, in very general case, must be equal to the applied forces. But in my case, I'm only interested in the natural frequencies, and although the system has some dry kinetic friction here because of the contact forces, but we are only interested in natural frequencies. That means I can ignore the damping forces, and this system is not forced, so I can ignore the external forces, so that the equation will be simplified into inertia plus spring forces must be equal to 0. The mass matrix will be diagonal, and the stiffness matrix, you look at M1, and M1 is attached to or connected to two springs, so the sum will be K1 plus K2, and the second mass is connected to two springs, K2 and K3, so you just put the sum in here. In between you have just one spring, it's -K2. Again, the system is free, so the right side of the equation must be equal to 0. Remember the video in the physical setup. Once you displace the card, from a distance, then the cards will just start oscillating, and then the amplitude of the displacement gradually decreases and eventually gets back to initial displacement to zero. However, assuming there is no damping force, you expect the card, once it's released from a distance, you expect the card to oscillate at the same amplitude back and forth at the same frequency. So this is my case, and the best representation of the signal will be in the form of some amplitude, displacement of the card multiplied by a harmonic function, cosine omega n t minus phi. Here omega n is the natural frequency and phi is the phase difference. And we just write the same equation for x2, which is the second card's displacement. So you need x, the position, plus the acceleration also. So you have to differentiate these terms twice. And there is something really important here. There is a really nice relation. Acceleration and position, they're linearly related. And if you write this as a matrix, so x1 double dot, x2 double dot should be equal to negative omega n squared times position. Remember, this was our mass matrix or mathematical equations. And wherever you see acceleration, you can plug in this equation, then multiply mass matrix with negative omega n squared. That will give you this last equation here. And we can still further simplify the equation because both of these terms are multiplied by the position. If you factor out by x1 and x2 in here, then I just get a product equal to 0. So let me just give you an example. If the product of two terms is equal to 0, then minimum either A should be 0 or B should be 0 or both of them should be 0. Of course, we expect some motion once we release the cards because the system is also undamped. So x1 and x2 shouldn't be 0, leaving us just one option. This matrix, this 2 by 2 matrix must be equal to 0 so that the right side of the equation will be 0. When we say this matrix should be 0, we mean that the determinant of this matrix should be equal to 0. So how can we solve the problem? And in this equation, as you see from here, there is no numeric value. This mass 1, mass 2, K1, K2, and K3, they are all variables. So let me just continue from here with the MATLAB code. We have to, let me also bring my notes, and you need to see this equation. It will help you. So we have to first define mass 1, mass 2, K1, K2, K3, and also omega n. And here, when you design the system, probably just omega n will be your only unknown. Here is my A matrix. So this is how I put how I define my A matrix after we define these terms as a symbolic variable. Remember, I was trying to find the determinant of this matrix. So we name it as A. And determinant of A, let's call it as DE, determinant of A. Let's calculate this. And from here, as you see, this is a fourth order polynomial. For a 2 degree of freedom system, we are expecting 2 natural frequencies, but mathematically there are 4 solutions. So let's solve this. The solution will be this, setting this determinant of A equal to 0 and solving for omega n. Yes, this is like a long expression here, but just to simplify it, let's give some examples. So for the sake of simplicity, I'm going to design a symmetrical system. Again, only for the simplicity. Here, let's say M1 and M2, they are equal to 2 kilogram. K1 is equal to K3, so it should be equal to, let's say, 400 Newton per meter. Because my mass is very small, I will use a very soft spring in between. Let's just select 200 Newton per meter. And from here, let's just continue. Then we will define our A matrix, and the only unknown, the variable should be omega n. Here is our matrix, and this is the only unknown in here. Here is A matrix with just omega n. Determinant will be just a fourth order polynomial in the form of omega n. And I'm trying to solve this matrix. But here, on purpose, I put double. If you don't put double, you will just see some of the equations in their radical form. Mathematically, there are 4 solutions, but physically we mean that the natural frequency cannot be a negative number. So I'm only selecting the positive value, so that let's say the first frequency in radian per second will be 20, and the second frequency will be 14.1421 radian per second. So I was trying to calculate the mod ratios of this system. So there are 2 frequencies. One of them, in our first case, if omega n is equal to omega n1, and in my second case, let me separate it. In my second case here, if omega n is equal to omega n2, and we're going to go back and plug that into our equation. And we named omega n1, we selected omega n1 and omega n2 from this solution, general solution. Now, how are we going to calculate the mod ratios? Remember how we named x1 and x2. x1 and x2 over the time should be equal to a1 and a2 multiplied by cosine omega nt minus 5. This is also from the previous page. If you plug in omega n1, wherever you see omega n in the A matrix, you will get to this matrix in here. So you have negative 200, here I'm copying this equation, negative 200, negative 200, and negative 200 multiplied by x1, x2, or instead I can just write this as a1, a2, and cosine omega nt minus 5. To make this equal to 0, the very first equation should be negative 200 a1, negative 200 a2 should be 0. And from here, negative 200 a1 should be equal to 200 times a2, so that a1 over a2, it should be just equal to negative 1. Remember, a1 and a2, they are the displacement or the positions of your cards. And similarly, if you plug in omega n2, wherever you see omega n in this matrix, you will get to the second form. Here I go back, you have 200, negative 200, negative 200, and positive 200 multiplied by a1 and a2, displacement of the cards, multiplied by cosine function, and this should be also equal to 0. My equation from here should be 200 times a1 minus 200 times a2 as equal to 0, and then 200 times a1 should be equal to 200 times a2, so that my second mod ratio will be just equal to positive 1. Remember, on purpose, I created a symmetrical system. So my first mod ratio is negative 1. Let's call this mod shape or mod ratio or eigenmod ratio. So mod ratio 1, and here is my second mod ratio. Let me demonstrate this. We have a 2 degree of freedom translational system connected by 3 springs. I have mass 1 connected to K1, then in between we have K2, and here we also have K3. Assume that, let me copy exactly the same sketch for the second representation, for the second mod, and let me put it here. If I displace, to be able to make the adjustment to negative 1, assume that I displaced the first card to the right by 3 centimeters, and I'm going to displace the second card to the same displacement but in opposite direction, so towards each other, so that x1 is positive 3 centimeters divided by x2 initial, which is negative 3 centimeters, that gives you negative 1. And in my second case, let's say I will move the first card to positive 2 centimeter and the second card also to the same displacement in the same direction, so that the mod ratio, the ratio of the initial displacement, should be equal to 1. If you displace the card to the same displacement in opposite directions, both of the cards will start oscillating at the same frequency, but this frequency will be omega and 1. And if you displace the card to the same displacement in the same direction, then both of the cards will start oscillating at the second frequency. And this is the summary of mod ratios. I hope you enjoyed this. If you want to demonstrate this phenomena, this theory in our virtual lab, please watch the next video. And thank you very much.